Okay, Assalamualaikum and good morning. So today, as I mentioned, I have a seminar at 10 o'clock. So probably, we just do only an hour. So we'll start very soon. Before that, I've also uploaded your assignment too. So your assignment too will help you prepare for test 2. So please try to do those questions and probably submit the next today is Thursday, yeah, next Thursday. Okay, right, so let's begin. Right, I think we have actually gone into lecture 12. So let me just remind you what it is. Essentially, we are looking at the cases of particles and collisions, and we've already gone into the idea of conservation of four momenta previously, and then we'll find that your idea about conservation of three momenta is included the idea of conservation of mass energy. So that was the fourth component part. Okay? So we have seen the relativistic energy defined as follows. So this is the relativistic energy. And from now on, your indices in your M over here, I will no longer write M naught. Okay. M naught used to be your rest mass, but now I will just simply replace by M. And if there are more than one particles, then I just use a subscript I. Okay. So we have gone to this part. Okay. Here essentially we look at the. Here I should write it as example case 1, where essentially what we do is to consider two particles with equal mass and then collide with each other to single particle mass capital M. Okay, so in other words, over here what you see in the beginning, you have your two masses plus some kinetic energy forming a single particle with single particle at rest. So there's no kinetic energy at this final process. Okay, and then what one gets in this particular case, you have this mass of the single particle at the end is greater than your mass of your individual particles at the beginning. Okay, so and then we talk about the mass defect, okay, which is delta M, and that delta M is actually coming from the contribution from your kinetic energy. We have seen that these two expressions are actually equal. Okay, so and then we look at another case. So what happens in the previous lecture, perhaps I was a little bit confused trying to apply a general equation, but essentially I should treat it as two different processes. So over here is another case of process of an atomic nucleus. So here you have your final product being a single particle like before. Okay, so this is a single particle at rest, and over here is essentially you have a particle in the beginning, and then you supply energy. Okay, and that supply energy is essentially a positive energy, so that it breaks down this initial particle into its constituents. Okay. So in other words, over here is a slightly different process than the one above. Okay? So I was slightly confused about the earlier lecture. Okay. So over here, what happens in this particular case, that your initial particle here is less than the mass will be less than the constituent particles thereafter, after the collision, so to speak. So this is in contrast with the one above. That was the confusion I had, okay, because it's two different processes. Okay, and over here, essentially, we have the other way around. So here is m less than sum of the sum of your individual masses. Okay, so it is for two different particles, two different processes. Okay, so this binding energy is, you will look at as if as a what you call a binding potential energy. So that is essentially the thing that one has to overcome in order for this single particle to be disintegrated into the individual particles. Okay, so here this process needs energy to break down into constituent particles. Okay. But there is another process, later on we will see about this. It's another process that sort of radioactive decay. You don't need to supply energy, and then it readily converts into the constituent particles. So that's a different process. But more or less, this is the kind of thing that you have to understand through equation of special relativity. Okay, so another common example that we have actually seen in probably in school or matriculation or STPM is the processes of nuclear fusion and nuclear fission. Okay, there are two different processes again. So this is the case 3 here, this would be the case 4. Okay, so what's nuclear fusion? It's coming from various processes. So over here is again just like the collision process. So this is like how should I say, it's like no, your earlier example of type 1 process, type 1 processes, but it's a composite. Okay, so you have two particles sort of colliding with each other to form a bigger particle, but there will be more particles in between, what you call as a how should I say, as a extra thing that's being involved in the process. Okay, so here is essentially what we call the hydrogen atom nucleus. So it's essentially it's a proton. Okay, you have a proton and proton combining to form I think this is called a deuterium nucleus. So it's just a hydrogen atom with, if I'm not mistaken, will be a 1 proton and 1 neutron kind of composition there. And then at this is deuterium nucleus, and this is a positron, and this is essentially electron neutrino. Okay, so these are not arbitrary. There are some conservation of quantum numbers that's involved. For example, here is what we call a lepton particle. Let me just write that down just for an extra knowledge here. Leptons are, for example, for electron and neutrino. So they have lepton number +1, but so this is an electron here. For the antiparticle, So this is a positron here, which is antiparticle to electron, and here is antineutrino, antiparticle to this neutrino. Here your L equals to -1. Okay, so here essentially you can see that what happens here, there's no leptons here. Okay, so the process before the collision is lepton number 0, and then you expect the end process will also have lepton number 0, and how we do that is to have lepton -1, lepton number -1 with a lepton number +1, and that gives you a lepton number 0. So but that's an extra thing that I'm just telling you about it. Okay, so in other words, these are not just arbitrary things that you put into the process. It comes from a certain interaction that is allowed by the particle physics. So here you'll see that the end product of this process will have this deuterium nucleus. Okay, so this deuterium nucleus will combine with another proton, or the hydrogen nucleus, to form a helium nucleus with mass number 3. Okay, and then in the process it also emits photons. So this is the symbol for photons over here. So in other words, this will actually you see some radiation coming out, okay, as photons carrying certain energies, and then the product of this process, you have a helium nucleus, and this will combine with another helium nucleus, because this is really not quite as stable as the ordinary helium nucleus. So this will combine with another 3 helium nucleus to form the stable one, the 4 helium nucleus. Okay, and in the process it also gives you 2 hydrogen nucleus, or 2 protons. Okay, so you can see that this is the kind of processes that that's also occurring in the sun, for example. Okay, so how the sun powers it up, the energy of the sun is coming from this kind of processes. Okay, so you can see that in the end you get back to 2 protons over here that sort of fits back into the cycle of this. Okay, so overall you find that all this reaction liberates about 26 mega electron volt of energy, and this is in the form of the earlier mentioned photons as well as neutrinos. So the neutrinos takes about around 0.3 MeV. Okay, so so this again an example of processes that has to be treated in a relativistic sense in order for you to be able to do calculations. Okay. All right. The next one is a nuclear fission. Again, you probably learn about uranium nucleus. I can't remember the mass number, but uranium nucleus is essentially unstable, so it decays. Readily. Okay, so this is slightly different from the process that we had earlier, the process 2, where you actually supply energy into the system, and then the system disintegrates into its constituent particles. So here essentially you don't need to supply energy, it's sort of disintegrate into to some other particles. So here is given in terms of M1, M2, M3 with some kinetic energy involving speed u1, u2, u3. Okay, so again in this process, if you remember, this is over here, this is different because you input energy, but if you don't have energy, then you see that your there's no, I mean, it's being unstable particle, so you still have your initial mass, the combined system being greater than your individual particles. Okay, so there is a mass loss given by this delta m, which is coming from the parent particle. Okay, sometimes it's called a parent particle. And all these particles are called daughter particles. Okay. So there is a mass loss going from parent particle to the daughter particles given by this quantity. And this essentially will be converted, okay, this amount of, remember that your mass is equivalent to energy, so the mass loss will have to be converted into something. In this case, it will convert into the kinetic energy of the three particles. Okay. So in terms of a calculation, you can actually do this. So you find out your disintegration energy for each what we call fission reaction. Okay. So all of this can be calculated. So we try to treat all these particle collision problems a bit more quantitatively using the concept of 4 momenta. Okay, the 4 momenta will include your ordinary 3 momenta plus the energy mass component, which is the fourth component. Again, I should mention, and in other books, probably in Faraoni as well, I'm not sure, I can remember the convention. The fourth component will be the zeroth component, so you have to be aware of these different conventions that takes place. Okay. All right. So how are we going to do this? Let's try to fix a particular convention of notation. So we'll consider those of before the collision. We'll consider those 4 momenta be given by capital P. So here is P I mu. So this is an I over here. P I mu, which is the 4 momenta of the incoming particle I, for example. So here's a diagram which has 3 particles going in and then 2 particles going out. Okay, so it can be, of course, more general than this. Okay, so your P will denote incoming particles and your Q will denote the 4 momenta of the outgoing particles. So we'll maintain this notation for sort of a convention, so that you have a specific standard naming of the we call naming of the 4 momenta of the particles in the process. Okay, so that's the sort of convention that we'll pick up as a notation over here and start looking at certain processes of interest. Okay, so here is the consideration of a particle, so decaying into 2 particles. Okay, so you have a particle at rest, so this is at rest, and then it decays to 2 particles which has what you call kinetic energy. Okay, and we denote the rest mass of this initial particle by capital M, and then your rest mass of your daughter particles given by small m with subscript 1 and 2. Okay, so the first thing we should try to do is to, okay, given the information that you have over here, what can we say about the 4 momenta? Okay, So in this case, remember the incoming particle is only this single particle. So there will be a p mu here. Okay. So this p mu, one should be able to write down in terms of components. So the first three components are the three momenta, but then you are given the condition that the initial particle is at rest. So I can just simply write 0, 0, 0. So the velocity essentially is 0 in the first three components. Okay, so then your three momenta is also 0. And then what about the fourth component? The fourth component is given by E or C, remember? But now the thing is at rest, so there's no kinetic energy contribution. So this is only your rest mass energy contribution. So that's capital M divided by C, just like E over C. Okay, so that's the first, the incoming particle. So the outgoing particles, again, one should be able to write down the components. So here you will have to assume some symbol for your momenta of the first particle, the Q1 mu. So we write as P1 vector here. And then your fourth component will be written as E1 over C. Okay. Same thing with your second particle. I will consider the three momenta by the vector P2, and then your fourth component will be E2 over C. Okay. So remember over here, this will include your rest mass energy contribution plus the kinetic energy. Okay. So we have seen that this is a kind of system which is a kind of system that we are thinking in terms of isolated system. So there you'll find that you need to observe conservation of four momenta. So in other words, this P mu must be, which is the one before collision. So there's no collision in this case. It's just a decay of one particle to two particles, but you can think of it as a collision process. So before collision is P mu. After collision, you have this two momenta. So you add this up to get your total four momenta, and then you get P mu equals to Q1 mu plus Q2 mu. Okay, and remember that now one can write this in terms of components. Okay, so the first three components will be this what you call the ordinary conservation of three momenta. The initial momenta is 0 because it's at rest. This must be equals to P1 plus P2. Okay, and then the fourth component is given by this. So that means the fourth component of your initial particle, okay, will be given by M over C, but let me okay, probably this is a mistake. Maybe I should have written down this as MC squared over C, sorry. Okay, so just take note of that. So this will be MC. Over here is MC, and it must be equal to these two addition of these two fourth components of the Q1 mu and Q2 mu. Okay, so you get that. So please be aware of that. Right, and then okay, so what do we do with this equations? Well, one can get more knowledge by noting that okay, each of these four momenta will have their own invariants. Okay? This must be observed. So for example, if I take the invariant coming from the particle 1, Q1 mu, Q1 mu, contracted with each other, this must be equals to your rest mass, okay, times C squared. Okay? So this you can check your earlier notes on four momenta. So this is minus m1 squared C squared. Okay? And this can be re-expressed in terms of the individual components. So remember, the individual components come from here. So contracting with the covariant counterpart of Q1 mu, so you get P1 squared. Okay, so the magnitude squared of the three momenta here, minus the fourth component squared, okay, which is E1 squared on C squared. And this must be equals to the invariant of Q1 mu, Q1 mu. Okay? So there you can rearrange these two, this equation here to show that your E1 is actually greater than M1 C squared. Okay, so this is just your relativistic energy. This is your rest mass energy. So in other words, your relativistic energy is inclusive of your rest mass energy plus your kinetic energy. Okay, and similarly, you can do the same for Q2 mu. Okay, so your Q2 mu will have an invariant given by minus M2 squared C squared, and in terms of their components, you have P2 squared minus E2 squared on C squared, and again we get essentially this similar inequality here. So if one remembers that you can actually write your capital M. Remember earlier we had this, right? So I can rewrite this as follows. Write capital M, so I bring the C onto the other side, so I get E1 plus E2 on C squared. Okay, and if you look at this thing, so here I can write this as E1 on C squared greater than M1, okay, and so on and so forth. So this E1 plus E2 on C squared, which is equals to M, is greater than M1 plus M2. Okay, so that's the first information that we have. So in other words, the bound particle in the beginning, before it decays, actually has a bigger mass than the what you call constituent particles that decays after. Okay, and then what else do we have? Well, we have the other equation, which is P1 plus P2 equals 0. So one can rewrite this, for example, in terms of a single notation. So P1 is equals to P, then P2 will be equals to minus P. Okay. So that's the well, this is this one is pretty obvious, but this is a consequence of using the invariance that we had over here. Okay. So what else can we actually do? Essentially, we can also rethink of your invariance in a different way. Here, we use the components of Q. Okay, over here we're doing Q2 here. So let me just refer to this Q2 mu. So we use actually the individual components of Q2 to get this what you call information. Okay. So let me write this differently because we have this equation earlier. P mu equals to Q1 mu plus Q2 mu. So I can rewrite Q2 mu as P mu minus Q1 mu. So in other words, Q2 mu, which I know equals to that, is equals to P mu minus Q1 mu, contracted with its coherent part. So I can expand this instead to get more information about the system. Okay, so here the contraction of P mu here, and then Q1 mu over here, and then we have the cross terms, Q1 mu P mu and P mu Q1 mu, which we can combine because this is just a scalar, so it's equals to the same thing. So you get 2P mu Q1 mu. Now with this, you can insert the individual components of capital P mu here, and also capital Q1 mu here, and also the cross terms. So you just refer back to the earlier components that we had, okay, over here. Oops. Then P mu will give you the invariant for the initial particles. That will give you minus m squared c squared. Q1 mu will give you the invariant for the first particle, which is minus m1 squared c squared. The cross term, you have to look at the individual terms. So here, remember the three momenta for P mu is 0 vector, and this has to be contracted with Q1 mu, which is given by this vector P. So you have 0 scalar product with P. And then the fourth component with a minus sign here, you have the fourth component of P mu. Okay, this P mu will be your MC. Okay. It's really MC squared over C, but it's this is just simplification there. MC, and then the fourth component of Q1 mu is E1C. So your C actually cancels off, and you're left with m minus m squared c squared minus 2m E1, okay, minus m1 squared c squared. So now what one can do is to rearrange this equation, okay, because what we have this must be equals to that. Okay, so we can rearrange it to get an expression for E1. And E1 can be expressed as follows. E1 is equals to c squared on 2m multiplied by m squared plus m1 squared minus m2 squared. Okay, so what's the good thing about this is the fact that, okay, I'd be able to calculate your energy of your first particle. The rest, you can see that this is your rest mass for your initial particle. This will be the rest mass of your first particle. This will be the rest mass of the second particle. So these are essentially known. So in other words, we can actually calculate the relativistic energy of the first particle. And you can do the same. So you just use Q1 mu, and then use the fact that Q2 mu, I should be writing Q2 mu, no, this is okay. Q2 mu is the one that we had earlier, so we are actually now considering Q1 mu, and then you re-express Q2 mu as P mu minus Q2 mu. Okay, so you do the same process with this thing, And then you should be again re-express your relativistic energy of the second particle in terms of the rest mass. Okay, so this can be calculated, and you can actually do quantitative predictions. There is a problem with this particular example though, so let's look at that. So now let's suppose we calculate the kinetic energy. So the kinetic energy is the relativistic kinetic energy is given by your relativistic energy minus the rest mass energy. So let's do it for the first particle, for example. So you have T1 equals to E1 minus M1 squared, M1C squared. And then you essentially put in your earlier expression for E1. So this is essentially the earlier expression is M1 M squared plus M1 squared. Okay. Let me check. So this is M squared plus M1 squared minus M2 squared. So this is coming there here, and then, oh yeah, sorry, I get confused with this capital M. So this is essentially coming from this term, but I'm putting out this common factor out of C squared on 2m, so I have the 2m multiplied for m1 here. Okay, so that's the reason why. So you have that, but I can now rearrange this as follows. I can rewrite this as capital M minus m1 squared, because I combine this, and that. So it gives you m minus m1 squared minus m2 squared. But this is just the form of a squared minus b squared. So I can rewrite this as a minus b, a plus b. So I can rewrite this as follows. Okay, so I have m minus m1 minus m2. Okay, your b is like your m2 here, and then m minus m1 plus m2. Okay, so over here we recognize this first factor here. This is essentially what we call the mass defect earlier. Okay, so this is delta m. For this, you can rewrite this in a different way. So it's a bit, I mean, one has to work backwards to actually convince yourself. So you can actually plug in this factor of 2 for m, capital M, factor of 2 for small m1. And what do we do? This factor of 2 is to cancel out the one in delta m. Remember, delta m is what? Delta m is m minus m1 minus m2. Okay, so the factor of 2 will cancel out your capital M here, and then small m1 here, so that will cancel out, and then I will get back to plus m2 here. Okay, remember that this is minus, so this I get minus capital M plus m1 plus m2. Okay, so I'll get back to this the same expression as put. Okay, so I can sort of simplify this into this expression. So here you have your mass defect, and then here's another factor which is showing you how to sort of related to the idea of a kind of relative mass kind of thing. Okay, So, okay, you can do the same for the other particles, which is T2. It can be expressed in terms of that. So, in other words, what we see here, that the initial kinetic energy is essentially zero because the initial particle is at rest, but you have the final kinetic energy coming from this relativistic kinetic energy T1 and T2 is not zero. So in other words, this process is not what we call kinematically favorable. Okay. Unfavorable. So really it's a nice pedagogical example, but it's not realistic enough. Okay? So what do we do in this particular case is to consider the case where your initial particle will not be at rest. So that's the next step. Okay? So one of the things that we can actually analyze is this idea of V particle decay. So what's a V particle? V particle is a type of particle that decays into why it's called V particle, because the initial particle is really almost invisible because they tend to be neutral. Okay, for example, here is I can't remember the name for this particle. Let's just call it lambda particle. This capital lambda. Okay. So this capital lambda has zero charge. It decays into two particles which has positive charge and negative charge. So you have electrical charge conservation there. And what else? So what's visible inside your detector are the ones coming from your charged particles. So you see these particles sort of producing tracks inside your particle chamber that looks like a V. Okay, so this is invisible. So that's why your lambda 0 here is called a V particle. Really what this is a composite particle consisting of an up quark, a down quark, and a strange quark. So this is what we call a strange particle in a more modern context. Okay. So this strange particle being neutral, so it's quite invisible in that sense, the tracks of it. But what one can actually see are essentially the electrical charge, the decay product of that particle. But the important point is that this lambda particle is actually in motion, so it's not at rest. Okay. So one of the question of this thing is, what is the mass of this particle? Okay. So these are some of the problems in particle physics. Suddenly you saw the decay products coming out from some process, and then you try to figure out what is this particle supposed to be. Okay. So here one can actually determine what the mass of this lambda particles. Okay. So what we do, again, we denote your for momenta after the so-called collision, if you like. So given by capital Q. So here is Q P mu, P representing the proton here. I should mention that this is proton. This is what we call a pion with a negative charge. There's a pion with positive and neutral case. Okay. So so you have Q P mu given in terms of components in this way, and then Q pi mu given in terms of component in this way. So what one can actually do is consider the case of the scalar that you get from the initial particle, p mu, and this is essentially given by the scalar of the mass of the lambda particle squared times c squared. Okay, so in other words, here already you'll be able to find some expression for your m lambda naught. Okay, and then what we can actually try to do is to use the fact that there's a conservation of 4 momenta. So this will be p mu equals to q p mu and q pi mu. Okay, so you plug this in and then form the necessary products. Okay, so here is q p mu, q pi mu. So this will give you, for example, q p mu gives you minus mp squared, the proton mass squared, c squared, and then this will give you the pion mass squared, c squared, and then you have the cross term again. Okay, so the cross term one calculates individually for each components. So you get p, pp, the proton, the proton momenta, getting confused with the two p's, proton momenta and the pion momenta dot product. Okay, and then the fourth component is the energies of the protons and the pion. Okay. So in the end, you get this thing to be equals to your m lambda squared c squared. Okay, so now you'll be able to get the expression. And if you look at all the quantities on the right hand side, this one you can actually determine experimentally. Okay, all of this, so you can actually calculate this. Okay, and the cross terms, for example, for this part, you can get that for your energies. You can get that from an earlier expression in terms of your kinetic energy squared and your rest mass energy squared. Okay, so that tells us that you can actually determine the mass of the lambda particle, mass of unknown particle. Okay, so I have 10 more minutes left, which I try to introduce you to the idea of another example which is very important, called Compton scattering. So Compton scattering is just the scattering of photons from electrons. So in the beginning, remember that your idea of electromagnetic waves, okay, in terms of wave, one doesn't really think of those electromagnetic waves behaving like particles. But you know that in quantum theory that you really have your electromagnetic waves, the constituent particles are essentially photons, and these photons interact in the same way just like any other particles. Okay, so in this particular case, you'll find that here is your initial momenta here. This is the one with the wiggly lines, essentially your photons. Okay, and the one with the what you call straight line, the solid line here, is your electrons. Okay, So here we have P1 mu representing the photons, and this is P2 mu. Okay, and then the process of the after the collision, you have Q1 mu. Q1 mu is your photons here. Okay, and then you have your Q2 mu, the scattering of the electrons. Okay, so let me just say that, okay, for the photons, remember, for photons, your rest mass of your photon essentially equals 0. So in other words, one of the simplification in this particular case is that you know that P1 mu is 0, and also the same thing as Q1 mu, because this corresponds to the photons, this corresponds to the photons. Okay, so that's a nice simplification. And of course, we also have the other one, but now it involves mass, but the mass of electron. So in other words, over here, P2 mu and Q2 mu, the scalar that you get from contracting it with the covariant counterpart is equal to the mass of electron squared times c squared with a minus sign. Okay, so we can use this together with the conservation of 4 momenta. Okay, so in other words, P1 mu, which correspond to your photon, plus P2 mu, which correspond to the electron, must be equal to the final momenta of your photon plus the final momenta of your electron. So one can write the components. Okay, one of the simplification that you get from photons, you can always write your components of your 4 momenta for photons in this way. So this is a vector, 3 momenta vector P, and this is the magnitude of the vector P. Okay, so then essentially what you get when you have P1 mu will be equals to P squared minus P squared, and that's 0. Okay, and the same thing for Q1 mu. So that is a nice thing that we can actually have for cases of particles with 0 mass. Okay? You can always rewrite this in terms of this simplified 4 momenta. Vector P times the magnitude, with the fourth component being the magnitude. Okay? For the electron, again, we just write it in terms of this. So here's the initial momenta for electron, and then you have your fourth component, which is given by the relativistic energy divided by C. Same thing over here. So over here, to differentiate from this initial energy, we write it as a dash. Okay, so the E dash here is related to this, and your E here is related to this. Okay. Right. I think I probably want to stop at this stage, so I just introduced to you only the notation, but we have not done any analysis of what's going to happen. So the idea later on is to be able to get a formula for your Compton effect. You probably have seen this in maybe modern physics or even matriculation or STPM, but normally these are given as it's sort of the formula is given to you without proper explanation. Here you actually derive it. Okay, you derive the formula for this Compton effect. So we'll do that. We'll do this in the next lecture. Okay. So let me take the attendance. Sorry about this because I do have a seminar that I promised to attend to my international colleague. Okay, I think that's it for today. So thank you everyone. By the way, please look up your assignment too and try to do it. Okay. Okay. Bye.